I'd like to thank the organizers for inviting me here today. It's a real pleasure and honor to be here. And I have to apologize that I can't do my lecture in Korean, even though I am Korean. I was born in Los Angeles and raised in the U.S. And just to tell you a very short story or background for me, growing up in the U.S. was difficult at that time. It was in a time where there were not very many Koreans there. Koreans were not well known at all. And I would be teased in school. And so the kids would ask me, "Are you Chinese or you're Japanese?" And they wouldn't say this in a very nice way. And I would say, "I'm Korean." And they look at me dissatisfied by my answer. And they ask me again, "Are you Chinese or are you Japanese?" And so just to have them stop bothering me, I would say, "Okay, I'm Chinese," and they would stop. And then growing up also, I came to visit Korea every few years. And during that time, every time I came to visit, I was always lectured by the taxi cab driver or by the ajumma on why my Korean was so poor. And after a while, I realized the trick to this all is if I just tell them I was Chinese, they would all answer to me saying, "Wow, your Korean is so good." So in the end, the irony of the whole thing is I ended up marrying a man whose last name is Sung. And as you know, Sung is both a Korean and also a Chinese name too. So everybody will continue wondering, or will not wonder so much why I have identity crisis. But anyway, I'm happy to be here to talk about my work and to talk a little bit about convergence. The title of my lecture is called Skin Deep, Changing Face of Architecture. And as I go through the lecture, you'll have a better idea of why it's titled that. I'm also a professor of architecture, so it's inherent in what I do to give you a background and context and a little history of architecture in a very short lecture in time. And then the second half, I'll talk about my work that I do as a researcher for architectural materials. So when I was in school, in college, I started as a biology major. And at that time, I went to a university that was a liberal arts university, and we were required to take courses in other disciplines. So I decided to take a class in architecture. And again, I didn't know my fate at that time. I was thinking that I was going to go to medical school. And I remember in my class, it was in a course that was the history of theory of architecture, my professor showed this photograph here. And this photograph is a 1931 Citroen car sitting next to a very groundbreaking piece of architecture at that time. Again, it's in the 1930s that this was built. And that groundbreaking piece of architecture, you may or may not know this one, it's the Villa Savoye by a Frenchman named Le Corbusier, was a very seminal moment for architecture. It was the moment that defined the modern movement. Before this, if you recall, all the houses and the structures were very traditional in nature. They had, again, the pitched roof, very thick walls. And what he talked about and wanted to promote was the expression of engineering, so that now that they had steel, the structure can be very thin, it can be lifted off the ground as if there's no gravity. The windows could be strip windows, they're not small anymore. And so it was a very big deal for architecture. And it was a culmination of his book that he wrote in 1923 called Vers une Architecture. And that book, translated into English, was called Towards a New Architecture. The word new was added in the translation, and it's a little controversial in itself, but still talked about this forward thinking of what architecture would be. And so in this book, he basically coined the phrase, "A house is a machine for living in." And so this stuck with me quite a bit, thinking, wow, this house was a machine for living in. How exciting is that? Well, the significance of that first photograph that I showed you with the car is the fact that that was probably the first time that architecture lived up to the automobile reputation as a piece of engineering. And the more important significant thing about that photograph is it was also possibly the last time that happened. So since then, the automobile industry has moved quite a bit forward, as you know. The engineering improved even more from that Citroen car the body becomes very streamlined as a reduction of the fluid dynamics necessary to reach a high performance for the car itself. And it's gotten to the point where even in this 2006, it's pretty old now, concept car for BMW, the body, in this case, could actually move and respond. It could change depending on the speed of the automobile across the landscape. And then the interior of the car also would change so that it would envelop the human body as you go inside. And so the combination of these things became one. The automobile became one with the human and an extension from that. And then, as you know, for the cell phone industry, once we went wireless and that we were able to make portable telephones, the development over time, in a very short amount of time, came to what we have now as these smartphones. The iteration was over just a very short period. Technology took off, and engineering was really on the forefront of everything. And so I show this image because there's the question that is put forth of where is our value system. Here we have a GPS system on the left, and we have a pair of hiking boots. And when you're up against a strenuous hike in front of you, the question is, do you choose the GPS system or do you choose a good hiking boot? And some of our value system will often say in a survey they would rather take the GPS system. And this is a dilemma because in architecture, so much of architecture is that physical manifestation of technology, and that technology in architecture has to move forward at the same rate. So when I Google high-tech home, this is the image that I get. And sadly to me, it has nothing to do with the architecture itself. The walls, the ceiling, the windows are basically the same, but high-tech is now embodied in just the gadgets that are shown here. So how do we look at architecture? How do we define it in a completely different way is what I basically ask. And high-tech, too, on buildings, oftentimes on the outside is defined by the gadgetry, too. These are just even bigger gadgets. They cover the entire surface, but architecture becomes just the armature for hanging these pieces on. And it has nothing to do how the building performs or how the skin performs on that building. So I'm going to go through a very short, very, very quick history of architecture and where we've come with that architecture. Again, the photograph that I showed at the beginning with the modern building, that's in the 1930s. And this building here, or these houses, were also done at the same time, right before that. Again, they're very traditional in nature. The thickness of the walls are very thick, and they were highly efficient for the time because they insulated the interior from the exterior so that when it was cold outside, the interior could remain warm during the wintertime, and when it's hot outside, it was still cool on the inside. And the windows performed quite well too because the windows were very small, so there was just very, very little heat or cold transfer through the system. So it worked quite well, and it worked through history a long time. But then with the 30s, again with this modern movement where it's all about the expression of architecture and the emergence of new materials like plate glass, like long spanning steel, came this new basic look. This came after the previous one I showed you. The plate glass now is from floor to ceiling. It is completely expressive of the architecture behind it, and it made man and the occupant feel very close to nature. You can look out the window and basically you could feel like you're in nature itself. But the problem with this is now you also let in a lot of sunlight, a lot of the exterior heat, and the walls thin to almost paper thinness. So you can imagine the interior can start getting very hot, and so therefore through engineering and a resolution of this, instead of moving away from this model, the intent was for people to want to keep this, right? And so instead developed all the engineering into mechanical systems, into air conditioning systems. And so over time, the engineering and architecture was going vertical, the anti-gravity attitude, where with structural engineering, we can make things high-rise like this. With the development of elevator systems and the further development of it could go even higher. And the window systems, right? All these things together allowed the mechanical heating, air conditioning systems to grow enormous in size, just absolutely enormous. So the problem is this: you have these very enormous systems, and we have, therefore, the use and the need for a high energy. So the energy systems itself is distributed as such, and they vary depending on what studies you're looking at. But the buildings themselves take about 40% of all energy used. It's distributed between the transportation, industrial use, but the buildings take up a huge amount. And within the building, too, you can see the further breakdown goes to HVAC systems. HVAC means heating, ventilation, and air conditioning. And so these systems, you can see, take 45%. The other part is lighting, and the last part, equipment. If we can make any kind of dent on that kind of energy uses, it makes a tremendous difference towards things like global warming and also for heat island effect. So the heat island effect, if you don't know what that is, it is something that also occurs in Seoul here and many cities around the world. It's a phenomenon where during the daytime, the heat is being absorbed by all the hard surfaces, right, all the city areas. And in the evening times, those hard surfaces start to radiate the heat out. By radiating it out in the evening, it basically raises the heat in a bubble around the city itself. And the differential between the temperature in the city at night and the adjacent rural areas could be up to about 10 degrees centigrade even. So it's a problem that we have in many cities. So the question is, how do we resolve these problems? We have these buildings that are very tall. In many cases, they're sealed because the windows can't even open in order for our mechanical systems to run efficiently. And what I like to look at, and this goes back to some of my biological early education, is why can't that building shell or that building skin be more like the human skin? Why can't architecture be the third layer beyond the human skin, clothing, and that's that building skin outside? So if we look at skin can do a lot of things, right? It can sweat in order to cool. It has goosebumps, and so it'll inflate in order to insulate. It's waterproof. It can make melanin so that it can react to the sun and have a response to that. It could do all these different things, including the regulation of temperature in your body, so that your heart and your lungs don't have to work so hard. And so if we equate the idea of heart and lungs to mechanical systems, right, the bigger and bigger need for that, why can't we look at the building skin as a way to reduce the need and the burden on mechanical systems? So I also like to, from my biological background, look at other systems of housing and biomimicry. And so one of the things that I look at is animal houses. And this is one of the animal houses that is highly insulated. It's a bird nest, right, from the social weaver bird. And it's built in Africa in a very hot climate. So you can see that this community for the birds is built on a telephone pole, which in some ways is very resourceful, in an area that there's very few trees in order to keep it cool and off the ground. It is waterproof, it is insulated, it is cool. Or in termite mounds. Termite mounds also are in Africa and other areas too, but these termite mounds are very interesting because they're built by, again, these very, very small insects. And if you look on the insides, there's all these tiny tunnels that go through the system. And what they do is when it gets too hot on the inside, they start to open some of the parts so that you can see some of the openings can be broken open here, can be broken up in the bottom, and you get ventilation through the entire system to cool it down. And they do it vice versa, too. If it gets too cold outside, they will close it up so that they can make it warm on the inside. And so we look back at houses, too. We look backwards to a very natural time and where things did actually work. We could look at systems and materials like water or ice. And the igloo is a very, very efficient system. They build these domes that are the simplest method of construction. It can take a lot of weight and a lot of lateral load from the winds. And it's obviously readily available and cheap. But the water bubbles, the air bubbles inside the ice cubes are able to insulate the interior tremendously. So the difference in temperature on the inside and the outside is really quite drastic. And then on top of that, when it's hot on the inside, whether it's from fire or from the heat of all the bodies, it basically allows this inside surface to melt, to seal all the cracks so that no air or snow can get through those cracks. And then there's other systems like the yurts, Mongolian yurts and other types of yurts, where they use goat skins or animal felts to line the tents itself. And they're porous, they're waterproof, and they're highly insulated on a very transportable level. But then we go back to architecture, and again there's the attempts to try to use architecture and build things on the outside to control that amount of heat gain on the inside. And so in these cases, this is a brise-soleil system in a building that was done in the 60s, and the brise-soleil system is built on the outside, and you can see that as a shading device to control the amount of sun that comes to hitting that glass that I showed you before. So it's a very passive technique. Passive meaning it doesn't need any kind of energy, it doesn't move, it's very static and very still. And here's a more recent example of the same type of thing where we have a large overhang for the ceiling so that the summer sun will not come into the window. And then the winter sun, when it comes at a lower angle, can hit that metallic surface and reflect inside to bring more daylighting inside and potentially heat too at a time when it's very cold. So there's techniques that we try to use in architecture that can do this, that don't require a lot of bells and whistles. And then in about the 80s, this is when active systems start to show up, right, where the active systems become moving, that they oftentimes required motors and a lot of energy to use too. So in this one, this is a project in the 80s that's done in Paris, and it still exists. The problem is it never worked from the beginning to this very day. In some ways, maybe it was the time and the engineering of it, but it was built too sensitive to operate properly, and so they finally had to shut it down. Perhaps if it was built today, it might work a little better, but these do require some amount of control and energy, as well as this one more recently, which you can see the windows and doors can actually open, and you can see by this pneumatic system here is done by controls and operated automatically. What I do is I use this new material, and my proposal is to try to make passive active systems. And I'll talk about that first and then talk more about this material. The passive active system I propose is trying to make things that are responsive, that can move, that can change, but require zero energy, that require no energy and require no controls to operate. And it's just looking at the behavior of the material, which we call smart. So the problem a little bit when we talk about and use the word smart is it's applied to many different things. Smart today is often applied to things that do require a lot of energy, but if you look at the true engineering meaning of that word, it is something that requires no energy and no controls. But the material that I use is a thermal bimetal that you see here and you saw activate here, and it's a very, very simple, very active material. It's a lamination of two metals together that's pressed, and they have different coefficients of expansion. So basically, when you heat the material will expand at different rates, and the actual action is a curvature. And the great thing about it is that it goes back and forth when you turn the heat up or turn the heat down. So what I'm going to do now is I'm going to show you just very quickly some projects that I'm working on. They're in very, very different levels. The work that I do ranges from art installations all the way to manufacturing components for the market. The thing in the middle is probably my part of where I'm most trained is as an architect and the application to architecture. So you'll see a full range of these types of things, and you'll also see it at different levels of development. So I have projects that are in the very basic science level and others that are getting closer to application. So this is one of the first projects using the material itself. I made a surface, and it's trying to use a lot of digital technologies and current contemporary fabrication technology into architecture. It's using laser cutting as well as some software that's used mainly for automobile design. But I was trying to make a surface that would move from being cold and flat to something that was very crimped and allow air to pass through in what I call a ventilating surface. So you can see here above is cold and flat. Here it'll allow air to move through, and the manifestation of it in the metal itself, and trying to make a surface. It changes from vertical to horizontal in what we call a very parametric model, and is a very complex and different way of looking at architecture. So here is the first prototype that was built. And you can see by the sequencing how the air and the heating of the surface changed. I also then tried to use it for shape changing. Architecture usually doesn't want to change shape. As you know, most times, like this building here, we want it to stay stable. We don't want our architecture to move all over the place, but it makes a very, very big difference in trying to understand responsiveness in design. And so these are some small tests of trying to make things move and change. And so in this one, it's actually a very simple tiling system. You can see the orange light on the inside is a heating device. It's an infrared heater. And so during the day and night, it would expand, because this one was in reverse. This was supposed to react to internal heat and be used at nighttime. This is one that we're working on right now. You can see it's a sphere. The sphere will open and close and will become transparent or solid. I'm not really quite sure. Again, someone asked me how I usually design, if I have a focus in the end to why do this, or if it's a bottoms-up approach, and I think in my work I do both. I have no idea exactly how this will be effective or useful, but I have good faith that it'll be useful someday. In some early models of it, the paper you see here is supposed to be where the thermal bimetal is used, and we use a lot of different materials in early prototypes to test that. I also did a sun shading canopy. This is the first one where it tested outside, and it was very significant because as an architect, if it's always indoors, if it has to do with the interiors, it has a very little impact to it. So the idea of this one was to build something outside that was more like a sundial. The top of it actually faces in a southwest direction where the sun is most intense, and the surface is designed so as the sun moves across the sky, the different parts of it will react in different ways. I show this one because it's kind of interesting. When we assembled it, we didn't anticipate how to use this material, so as we went through the sorting process, in the middle of the day, everything curled up, and it was really quite difficult to deal with this material. But in the end, I show you some photographs of here. There's about 14,000 different pieces in this entire model, and no two are alike. The structure is also fairly significant. The digital models we used very quickly determined how long these curling pieces would be. In some cases, they'd be short, where we didn't need any reaction because everything was in the shade. In other cases, the top portion was thicker so that we didn't want any light, and we wanted to control the amount of light coming through. And so you can see here in, again, early paper prototypes of the tail, how we were able to get more structural surface out of it. And some of the digital modeling with analysis tool with solar connections, right? The sun would only hit those areas in the red here, and the areas in blue would never see direct sunlight at all. Here's some just day and night photos. And here's a video just quickly of the surface. You can see as the sun moved across the sky, the shade moves across the surface and really made a change. So this was very, very significant in one of the first models that we built, and this was built in 2011. Sorry, it's going very slowly. Okay, now it's stuck, sorry. The shade actually moves across, and all these pieces fold down really nicely. Here it is from above. The idea was that it would be put on basically on the outside, like the Brise Soleil system. Here was a design for a Chinese house, a very large one that you can see in the red is a glass tower, and the bimetal surface was supposed to be put on the outside. And you can see here a projection of it where that bimetal surface can control the amount of sunlight coming in so that they would use less air conditioning in this house itself. It also was able to use as a privacy screen so that they needed no blinds and no curtains at all. I also used it on other systems. This is a sidewall breathing system. Looking at a grasshopper here, you can see A grasshopper breathes through these holes in its side. You can't see the holes itself, but the way that they bring in air is by contracting their diaphragm, and it comes in these spherical holes through the sides here, and then the air moves around this wall system. And so the idea behind here is, why can't architecture possibly work like this too? If we have a thick wall system, why can't we move air around the wall system in order to keep the interior and exterior cool? It's also using the Venturi effect, or Bernoulli's principle, where by changing the section of it, we can pull and suck in air faster or push it out at a different speed. With early models of trying to make this wall, again using these digital tools to control and vary a surface, and allow air to pass up through a system in a much more complex way. So this is again an idea for a cinder block type of wall using new technologies. Here's the bimetal as a valve system controlling the amount of heat getting through. The red light is part of an infrared heater. And a short video again, you see the red light coming on, that's the heater coming on, and as the heat moved up through the system, you can see each of the valves opening and closing too. I'm working on some things for components for the market, as I mentioned to you before. These are window systems, and hoping to get to some window shading. The typical problem, as you know, as I mentioned before, is that we have a lot of glazing, right? We have a lot of glazing on these south-facing walls where the sun could come in, and on the inside we get a lot of heat coming in and have to use a lot of air conditioning. So the proposal is trying to use this bimetal within the windows itself that require, again, no energy, no controls, so that as the sun comes across the surface, it automatically closes and is able to control the heat from coming inside. Right now I'm working on different kinds of patterning systems. They're very complex in nature, so that you can see a perforated surface from here on the left, which you can see through at a distance, then starts to open up to be even bigger. And here's some very early videos of these kinds of surfaces changing, opening and closing. And it has a big effect on what architecture is and how we see it. So the outside of a building then starts to become what the operation of that surface is. The performance of that wall starts to imply what a facade becomes. And here you can see an interior view. We're not really quite sure about the scale of these patterns yet. Here's a scale that's really quite big. But the idea that we're trying to do is move it to a micro level, so that possibly all you can see is just a filtering effect of these systems before and after. I also have structuring surface. I just have a couple more I just want to show you real quickly. This is an exoskeleton, trying to use that bimetal in a completely different way during the assembly process and trying to make a matte surface that's strong. And so you can see here the pieces are curled when heated, and heated at a very high temperature, and when they're curled can be inserted into place, and as it cools down it'll try to flatten, and what happens is it makes a pre-stressed surface and a very strong surface in that. And by controlling the different curls or curvatures of the bottom and the top, we can make it either convex or concave. And the application in this one is supposed to be built and completed by January 5th this new year. This one's about 15 feet tall. It's going to be its own structured system and will be shown soon after that. The last project I'm going to show you is a tensegrity project. And tensegrity basically means something that's a combination. It's a structural system that combines both compressive units as well as tensile. And you can see they never actually touch each other. The compressive units only touch a tensile unit, and a tensile unit touches a compressive unit. And it's, again, with the biology thing, it's related to, in this case, the muscle system. There's a combination of muscles, bones, and tendons that are needed for a heel, in this case, or anything in your body to work. And so the idea is that this would be the same thing in this case. And so what I use as part of that is this material nitinol. And nitinol is a material that's a wire, and it's similar to bimetal in that it reacts to heat. So this is a bowl of hot water, and as it goes back in, it has this memory to return to its original form. And so the idea is that the nitinol would be used in combination with the bimetal. The bimetal will be the gray surface that you see in this diagram. The rubber bands, or part of the rubber bands, would be the nitinol. And so the combination of it reacting to heat would make something change or rotate. And in this case, it would be a canopy system, so that the canopy system can rotate relative to the heat in the most optimal direction to that sun. And here again, in early models of just changing very few and limited number of wires and the length of it, able to make a contortion actually happen. And so this is a very big deal for structure. So basically, I want to leave you with 3 thoughts, and this is the stuff that possibly has to do with the convergence. One is that architecture should and can be passive and active. Instead of thinking of ways to just shade or thinking of ways to just make things active, we need to make things that are highly technical but require zero energy and no controls, because we need to make a bite into that energy system and worry about our future and global warming. The second thing I would say is to really look at smart materials for architecture too, because there are many smart materials out there. It's just that we somehow are backwards and slowed down by the ability to use them. So smart materials, I think, is a lot of what we can do. And the last thing to think about is, instead of architecture being the machine for living in, that maybe it should be more like the organism to live in, that somehow it needs to be thought of holistically. And if you take all these things together, the convergence, at least in architecture, is something that's more than a paralleling or coming to a point, but actually a collision in itself. So thank you very much.